This is the second video in the lessons for section 12.5, and this deals with a little bit more application for trig functions in simple harmonic motion. This first example here, suppose you ride a Ferris wheel, a rather small one, 30-foot diameter Ferris wheel at a local carnival. You start at the position -pi/2, so you start at the bottom to get on. That kind of makes sense, right? And you rotate counterclockwise in the direction uniform angular velocity, so it's not a jerky ride, and you do 1 revolution in 60 seconds. So if you look here, as far as the Ferris wheel goes, it's a diameter of 30, so you've got 15 up and 15 down, so you're actually starting at a position of -15, and down here at -pi/2. So our amplitude is kind of the easiest things to figure out. That's going to be our 15. We go up 15, down 15. If we had been on a platform or something, for instance, that would shift our midline up. That would not shift our amplitude, but it would shift our midline. And in this case, our phase shift, our theta here, is going to be -pi/2. That's going to be our angular displacement. The only thing that's going to be a little more complicated to find is our angular velocity. Our angular velocity is going to be our revolutions over time. So omega, again, is going to be in radians per second. We have revolutions per second, so 1 revolution per 60 seconds. Again, a revolution is not radians. It takes 2 pi radians, or a full rotation, to go 1 revolution. So we're going to multiply by 2 pi per revolution. And we end up with pi/30 if you wanted to, radians per second, which is what we need for omega. So if you recall our formula, y is equal to a times the sine of omega t plus theta. We now have everything we need. So in this case, y is equal to 15 times the sine of omega is pi/30 times t, and then our angular displacement here is -pi/2. So when we go to graph this, we have our amplitude is 15, our period is 60. We knew that from the original problem, or we can do 2 pi divided by pi/30, which will give us 60. Our phase shift is -pi/2 divided by pi/30, which, if you simplify, you get -pi/2 times 30/pi, which you can see reduces to -15. So that's our phase shift. So that tells us our starting point is at x equals 15, which means our ending point is going to be at x equals 15 plus our period 60, or 75 seconds. Again, these are all in seconds. So our units for x are in seconds, y is in feet. We can label our axes. We've got 5, 10, 15, 5, 10, -15. We'll go by 5s also as well on the axis. It just so happens that both things ended up being 15. So we got 15 here, 30, 45, 60, and 75 for our ending point for one cycle. So again, sine is going to start at 0, going to go up to our amplitude 15 at 30, going to go back to 0 at 45, our halfway point, going to go to -15 at our 3/4 point, and then back to 0. So we fill in our sine function. And again, we have this midline because we weren't on a platform or anything like that. If we had been on a platform to get up off the ground, we would have to have this shifted with a vertical shift. If we want to go backwards, which is what I would recommend as far as this graph goes, we got to go back. So we've got 0, we would have -15, -30, and then we'd have -45. So that gives us our quadrant. So at -45 we're at 0, At 30, we're up here at 15. At negative 15, we're back at 0. At the y-axis, we're at 0, which makes sense. That was where our height was when we started the ride. We were at negative 15 from the center of the Ferris wheel. So we can complete this cycle. And this makes sense with everything. Again, we started on the ground at negative 15, and so that's where our graph here crosses our y-axis. So let's answer a couple questions about this. How far in radians does the Ferris wheel travel in 45 seconds? Well, you can kind of intuitively guess this, or you can just look at the omega t part of the graph. So omega was pi over 30. And then we've got times t was 45. So we end up with 3 pi over 2. So that's how many radians it has gone, which makes sense. If you think about where we started, you've got 1, 2, 3 quadrants that you've gone through. So 3 pi over 2 is where we end up. So that's how far it's turned. Okay, if we want to find the height that the Ferris wheel is at after 45 seconds, we plug everything into y. So y is equal to 15 times the sine of pi over 30 times 45 minus that pi over 2. And when you do all this, you should end up getting 0, which makes sense as far as height goes. As far as your location on the Ferris wheel, you started here down at negative pi over 2. This would be a height of 0 because this is negative 15 and this is positive 15. If we go 45 seconds, we've gone 3/4 of the way around, or that 3 pi over 2 rotation. We've ended up here at pi, and that is at a height of 0. So let's look at a couple more examples here. A particle moves in simple harmonic motion with a frequency of 5 oscillations per second and an amplitude of 2 centimeters. So they tell us our amplitude here is 2, and that our frequency here, now we have F, is 5 oscillations per second, sometimes known as hertz. We know that omega is equal to 2 pi times F, so if we plug that in, we've got 2 pi times 5, which is 10 pi. So our equation for this function is going to be 2 times the sine of 10 pi times t. In this case, we have no change in displacement, so our angle would be 0 for adding it, or you can just leave that blank. Through what total distance does the particle move during one cycle of motion? So this is where you have to be careful. Plugging in one full cycle is just going to get you back to 0 because it's a sine function. You have to think about what's going on. Sine function is going up and back down. So it's going up 2 centimeters, down 2 centimeters, down another 2 centimeters, and then up another 2 centimeters. So if you put all of those together, you have a grand total of 8 centimeters that this particle has moved through, up, down, down, up, to get to the end. Let's try one more example here. An AC generator produces a voltage which varies according to the following equation. V is equal to m times the sine of omega t plus theta. Looks very familiar, only difference is A is now m, y is now v. V is the instantaneous voltage at a time t, m is the maximum voltage. Suppose you have a generator whose max voltage is 10 volts and operates at a frequency of 50 hertz. Again, remember this is our frequency. That is oscillations per second. Phase angle of pi over 3. This should be kind of moved down here. We want to find the equation of the curve described by the problem. So again, in this case, we are told our amplitude, our max voltage, was 10. We know our frequency is 50 hertz. And we know that omega is 2 pi times our frequency. So we end up with 100 pi as our omega. And finally, they tell us our phase angle is pi over 3. So y is equal to 10 times the sine of 100 pi times t plus pi over 3. This one is a little bit more involved as far as graphing goes because we have that 100 there. Our period is 2 pi divided by that 100 pi, so we get back to that 1 over 50 that we were talking about. Remember, period is the reciprocal of the frequency, 1 over 50. Our amplitude, we already said, was 10. That's not too bad. Our phase shift is pi over 3 divided by 100 pi, so we end up with 3 over 100. So we end up with 1 over 300. So we got 1 over 50 and 1 over 300. If we go by 300ths as far as our units go, so 1 over 300, that's a positive in this case, so we are going to have our starting point at negative 1 over 300. And our ending point is going to be at negative 1 over 300 plus our period, which was 1 over 50. That gets you to 5 over 300, or 1 over 60. So that's going to be our ending. It's kind of maybe easier to look at it as 5 over 300 since we're going by 300. So there's 1, there's 2 300ths, there's 3 300ths, or 1 100th. There's 4, and there's 5 300ths, or 1 60th. Again, we need to go backwards as well because we're actually starting at negative 1 over 300. Amplitude is 10, so we'll make this 10, this negative 10. Again, we're dealing with a sine curve, so we're going to start at 0. We're going to hit our amplitude at our quarter mark, which in this case is the axis. We're going to cross back at 1 over 300. So we have to be really careful with our half and quarter points. Our halfway point here is actually at 2 over 300. So you can see you'd have 1, 2, 3 to get there, and 1, 2, 3 to get to the end. So that's the halfway. The quarter point's going to be here at 1 over 600, and here as well. So again, sine function is going to start at 0. It's going to hit our amplitude at our quarter point, which is right there, 1 over 600. Cross at the halfway point at our midline, down here at our negative amplitude at our 3/4 point, and then back to our midline for our ending point. So we can draw in one full cycle for our graph there. So this concludes the video for section 12.5.